You've now seen how words got vectorized. 9 videos of the specific ideas that turned a symbol into geometry. Vector arithmetic, distributed representations, V04 GloVe, the distributional hypothesis, cosine similarity, polysemy, contextual embeddings, evaluation and bias. It's all in your head now. Next, how stacking many of those vectors into deep networks gave us GPT. This is the recap. Fast, pointed, 9 videos of Lecture 5 in 10 minutes. Then a preview of Lecture 6, where embeddings stop being the endpoint and become the input, RNNs, LSTMs, transformers, BERT, GPT, the deep learning explosion that took our vectors and gave us modern AI. Last video I walked how to evaluate embeddings, analogies, similarity, downstream tasks, and the honest problem. Embeddings absorb the biases in their training text, which is a fitting way to close a lecture on how computers learned meaning, because they didn't really learn meaning. They learned the statistics of usage, and that's most of what meaning is. Here's today's puzzle. Every video of Lecture 5 was about how to turn a word into a vector that carries meaning. But a vector by itself doesn't build ChatGPT. To get from a good word representation to a machine that writes like a person, you need to stack those vectors, feed them into layers, let the layers learn what to do. That's Lecture 6, and it starts with a small idea called the recurrent neural network. Today's 3 beats. First, the 9-video walk of Lecture 5, what you should remember. Second, the running theses, every big idea from L5 in 1 line each. Third, the bridge to Lecture 6, where we take these vectors and stack them into the neural networks that make GPT. Beat 1, the walk. Video 1, the embedding magic trick. Mikolov 2013, king minus man plus woman lands on queen, meaning as a byproduct of co-occurrence. Video 2, from one hot to distributed. Bengio 2003, every word its own dimension gave way to dense vectors where each dimension is a latent property. Video 3, V04 VC, Mikolov's actual algorithm, CBOW, and skipgram, 2 shallow neural network architectures that trained fast enough to change the field overnight. Video 4, GloVe, Stanford's answer, global co-occurrence statistics factorized directly. Same result as V04, different math, better on some analogies. Video 5, the distributional hypothesis. Firth 1957, you shall know a word by the company it keeps. The linguistic theory from before there were computers to test it on. Everything that follows leans on this one sentence. Video 6, cosine similarity. The specific way to actually measure closeness between 2 vectors. 5 lines of code, runs every semantic search on the internet. Video 7, polysemy. The bank problem. Static embeddings averaged all senses of a word into one muddy vector. 10 synsets of bank, 1 point in space. Search engines mixed rivers with vaults. Video 8, ELMo, Peters 2018 at Allen AI. Contextual embeddings. Same word gets a different vector in every different sentence. Polysemy dissolved. 6 state-of-the-art benchmarks fell in a single paper. Video 9, evaluating embeddings. Analogies, similarity judgments, downstream tasks. Linzen 2016 showed the analogy benchmark is way weirder than it looks. The score depends on excluding the input words. And Bolak-Bossi 2016 showed the vectors absorb gender and racial bias. Embeddings are mirrors of the internet. Now the theses. The one-liners you should walk away with. 1. King minus man plus woman equals queen. Meaning showed up as a byproduct of co-occurrence. Nobody programmed it in. 2. One-hot encoding is a 50-year mistake. Distributed representations put meaning into the geometry. 3. V04 was the earthquake. Skipgram and CBOW. 2 architectures, trained in hours instead of weeks. 4. GloVe, same result as V04 via a completely different route. Direct factorization of a global co-occurrence matrix, which is a lesson about what the data is actually giving you. 5. Firth 1957, you shall know a word by the company it keeps. Everything downstream leans on this. 6. Cosine similarity, 5 lines of code, runs every semantic search on the internet. 7. Polysemy. Bank had 10 meanings. Static embeddings averaged them into 1 point. 6 decades of word sense disambiguation stalled at 75%. 8. ELMo 2018. Contextual embeddings. Sentence in, vector out. 6 benchmarks fell overnight. 9. Evaluation is task-dependent. Good embeddings are honest embeddings, and honesty includes bias audits. Those are the 9 ideas. Beat 3. The bridge to Lecture 6. You now have vectors that carry meaning, but a single vector is just a point. To get GPT, you need to stack those vectors and feed them into layers of learned transformations. Recurrent neural networks, the first attempt to handle sequences. LSTMs, the fix for what RNNs got wrong. Transformers, the 2017 paper that made everything scale. BERT and GPT, 2 flavors of the transformer. And beyond that, the giant models running your favorite AI product. Lecture 6 walks the whole story. 10 videos of the deep learning explosion that took embeddings as input and gave us modern AI. 3 takeaways before the quiz. 1. Lecture 5 was the story of how a symbol became geometry. Distributional semantics turned words into vectors that carry meaning. V04 GloVe ELMo. Simple ideas, deep applications. 2. Every modern language model uses embeddings as input. The vectors we walked in this lecture are literally the first layer of GPT, not a metaphor. The actual first layer. 3. Lecture 6 stacks those vectors into deep networks. RNNs, LSTMs, transformers, BERT, GPT. The layers that took our meaning-shaped inputs and gave us machines that write like people. Quiz 1. What's the one-line summary of Lecture 5? A. Embeddings are hopeless. B. Words became meaning-shaped vectors via co-occurrence, static then contextual, with real limitations. C. Only Chomsky matters. Or D. One hot is best. B. The whole arc. 9 videos walking from Mikolov's 2013 vector arithmetic magic trick through Bengio's original 2003 distributed idea, through V04 and GloVe, resting on Firth 1957's distributional hypothesis, measured with cosine similarity, blocked by Polysemy, unblocked by ELMo, and honestly critiqued by Linzen and Boluk-Bassi in 2016. That's Lecture 5. Quiz 2. What connects Firth 1957, Bengio 2003, Mikolov 2013, Peters 2018, and Boluk-Bassi 2016? A. They are unrelated. B. All 5 gave the embedding story a pivot. C. Same paper. Or D. They all predicted transformers. B. 5 pivots. Firth wrote the hypothesis 50 years before we could test it. Bengio built the first dense embedding but was too slow. Mikolov made it fast and unlocked the whole field. Peters made it contextual and set the transformer stage. Boluk-Bassi held up the mirror and showed us what our vectors had absorbed. Each pivot moved the story forward 1 step. Quiz 3. What's Lecture 6 about? A. More word embeddings. B. Deep learning. RNNs, LSTMs, transformers, BERT, GPT. The layers stacked on top of the embeddings from L5. C. History of Stanford. Or D. More Firth. B. Deep learning. Lecture 6 takes the embeddings you just learned and stacks them into the neural networks that became the modern era. RNNs, to handle sequences. LSTMs, to fix what RNNs got wrong. Transformers, the 2017 paper that made everything scale. BERT and GPT, 2 flavors of transformer. And beyond that, the giant models running everything. 10 videos of the deep learning explosion. Back to the puzzle one last time. Lecture 2 showed you words. Lecture 3 showed you what words do in sentences. Lecture 4 gave you the math toolkit. Lecture 5 turned those words into vectors of meaning. And now, Lecture 6 stacks those vectors into deep networks. And out the other end comes ChatGPT. Next lecture, deep learning. RNNs, LSTMs, transformers, BERT, GPT. 10 videos of how stacking embeddings into networks gave us the modern AI era. The deep learning explosion that turned this whole course's toolkit into machines that write like people. hit subscribe, and I'll see you in Lecture 6.